Hello everyone. In this video, we shall discuss multiple integrals, the double and triple integrals. Before going to the definitions of double and triple integrals, we shall revisit the concept of definite integrals. Definite integral a to b f of x dx represents the area under the curve y equal to f of x between x equal to a and x equal to b. The area under the curve y equal to f of x is divided into small rectangular regions, and the sum of the areas of these rectangles will approximate the area under the curve. Hence, the area under the curve is the Riemann sum of the area of the small rectangles. Hence, integral a to b f of x dx is equal to limit n tending to infinity of summation I equal to 1 to n f of xi into delta x. The same idea is extended to double integrals. Prior to defining multiple integrals, we shall just recall the volumes of some regular solids which we have learnt as formulae in our high schools. What is the volume of a cube with side d? We all know it is d cube. What is the volume of a cuboid with dimensions L, B and H? It's L into B into H. Similarly, the volume of a cylinder is pi r square H. The volume of a sphere with radius r is 4 by 3 pi r cube. The volume of a right circular cone is pi r square h by 3. Now, can you tell me the volume of this irregular solid? That is, can you find the volume under the irregular surface over the rectangular region in the xy plane? Let us consider the graph of the surface S, whose equation is z equal to f of x comma y, defined at every point on the rectangular region R, bounded by a less than or equal to x less than or equal to b and c less than or equal to y less than or equal to d. We shall find the volume under the surface S over the region R. We will divide a less than or equal to x less than or equal to b into n number of subintervals and divide c less than or equal to y less than or equal to d into m number of subintervals. This division makes the region R into m into n number of small rectangular regions. Let xi, yj be a point in the ijth rectangle. Over each of these smaller rectangles, we will construct a box whose height is given by f of xi, yj. Each of these rectangles has a base area of delta A and a height of f of xi, yj. Hence, the volume of each of these boxes is f of xi, yj into delta A. Thus, the volume under the surface S over the region R is approximated as Riemann sum of elemental volumes, that is, V is approximately limit n, m tending to infinity of summation I varying from 1 to n and j summation j varying from 1 to m of f of xi, yj into delta A. This looks similar to the definition of integral of a function of single variable. Thus, the definition of a double integral of a function of two variables over a rectangular region R is given by double integral over the region R f of x I, y f of x, y into dA is equal to limit n, m tending to infinity of summation I equal to 1 to n summation j equal to 1 to m of f of xi, yj into delta A. Here dA is dx into dy. Therefore, volume V is equal to integral double integral over the region R f of x, y into dA is equal to double integral over the region R f of x, y dx into dy. Now we shall see how to evaluate the double integral. Since the region R is bounded by the lines x equal to A, x equal to B, y equal to C and y equal to D. X varies from A to B and y varies from C to D. Therefore, double integral over the region R of f of x, y into dA is equal to integral A to B integral C to D f of x, y dy dx. Let us see how we can evaluate this double integral. We first compute integral C to D f of x, y dy, keeping x a constant and integrating with respect to y between y equal to C and y equal to D, which results in a function of x only, say g of x. Then this function g of x is integrated between a and b with respect to x, which results in the required volume V under the surface f of x, y over the rectangular region R.